Okay, now recording is on, I hope. Hopefully this gets recorded well as I plan to. Anyways, let's get started. Looks like the other student is unable to come in. There's a little issue with the link. I'm not sure why. We have three students here. Huh. Anyhow, okay, so we are going to start with the nomenclature first. Okay, so nomenclature basically means a naming compound. It's nothing too serious about it. Remember last week we talked about covalent bond and ionic bond, right? So there are two ways to name things depending on what kind of bonding it is. So when we are looking at the periodic table, let's take a look at periodic table first. Open up my chart. Okay, periodic table. There you go. All right, okay, so we are basically talking about the main two groups in a periodic table. Hold on a second, there's a message I was hoping to go over, figure out how to determine the geometry, shapes, and angles. For Ash, that could be possible. I was actually asking by Professor Chai that you guys are having an exam regarding a nomenclature mole concept next week. So I'm gonna cover that first, and if time allows, I'll go over that geometry and shapes and angles and whatnot. Okay, so that also actually kind of no, not a problem. Yeah, so that will actually go into a little more in depth of what we've been learning so far, but definitely we can try to go over that. Okay, so let me actually start with this first. Well, but then, okay, since you're the only one as a college student here, are you okay with the naming compounds, nomenclature, and mole concept and balance equations? Because if you're okay, I can go straight to your topic first and then go back to the naming compound and whatnot. Okay, so you're comfortable with all those three contents basically, right? Okay, sounds good. Then let's go straight into our geometry shapes. Okay, and whenever it is, because of the other student who may want to listen to the those three topics, we're gonna start with that afterwards. Okay, so let me actually pull out my lecture book. Okie dokie. So, vertical view, navigation plane. Trends. There you go. Okay, so basically all this structures and whatnot is generally mostly geared into uh, uh, a lot has to do with non-metal compounds basically, which is covalent compounds. I mean, there are crystalline structures that has to do with the metals, but I don't think you are going into that depth of it. But when it comes to geometric shapes and angles, we're generally talking about the non-metal compounds. Okay, so let's go with the very basic first. Okay, and last week we talked about like a carbon dioxide, carbon monoxide, and whatnot, right? So let's kind of go briefly into that and go into a little more into depth of the other topics. Let me get rid of this one first because this does not cover too much of that. So let's go into our geometric shapes. So we were looking into a carbon monoxide, which looks like this, right? Right? Basically, give us a little shape that kind of gives us there is nothing you can be done except it's what a linear shape, right? So this is basically a linear, right? So when it comes to this, I guess a two-dimensional drawing is like a stick figure. It's kind of easy for us to kind of figure such a way, but when it comes to actual three-dimensional drawing, something you actually have to focus on is how it's actually started forming that stick figure. I mean, I know there's only two things in there connecting together, but there are actually literally a geometric shape behind it. So let me actually make it sure a little bit more of a three-dimensional drawings. So we have that. Oops, let me get rid of that. Okay, we have this. Okay, and then may not be the most accurate, but it will do the job. Okay, I'm trying to. That's way off. Okay, let me go a little bit behind it. Okay, there you go. Okay, so you probably already kind of tell that this is like a x-axis, this is y-axis, and this is z-axis, right? So this is on a plane, x and y, but z gives us in depth of it. Okay, so basically what happens in the bonding when it comes to bonding is, and this is actually probably a topic that may not be touched or may be touched in your class too, but then I'm gonna just kind of briefly go into it. When they're forming a bond, each orbital, remember when we were looking at the periodic table, we were looking at this SPDF last time we were doing the electron configurations, right? Right. So here we have a uh, uh, S here, P here, right? D here, and F here, right? So SPDF, and we was in 1s2, 2s2, and all that stuff, right? So basically what this tells us is that when we are talking about S, that has to be with orbit, or like orbitals, where electrons are spinning around, right? So when it comes to S orbitals, they're basically a sphere shape, okay? When it comes to P, remember P, we actually have what? 6 electrons can fit in there. That's where we have an X, Y, and Z axis come in, and each orbital has a y-axis orbital in that, like, loop shape, right? And then there is a x-axis, and then there's a z-axis, right? So this is where we are actually, where the electrons are supposed to be found when we're looking at these p orbitals. So when it comes to a bondings, we're gonna I mean, this, like I said, this is more into a whole lot more deeper topic than what this meant to be. But briefly speaking, when we are bonding each other to the S to the P to the P to the S, or S to the S, the P to the P, doesn't matter. They actually overlap these little loops each other, and then they come in together as a bonding, meaning that electron that one was here, let me give you a different color, electron that was in on this one will try to bond with that electron, pair up with that electron, and come in together as an overlapping together. We call that hybridization. So when there is a overlapping of s orbital with the p orbital, we call that sp hybridization. Okay, so this bonding between two electrons, like I said once again, with the involvement of two electrons, has to with a these each individual bondings that we represent here. Okay, so I'm not going to go too in depth of it, just a little brief why we are drawing this first. Okay, so when we look at carbon, carbon has, okay, they had a carbon of 4 valence electrons, right? And then oxygen has 6 valence electrons. Okay, and those are arranged in such a way they are forming a triple bond to each other to have a what? Octet of carbon, right? Carbon has 2, 4, 6, 8 carbons, electrons, right? So which is happy. For oxygen VU2, we have a 2, 4, 6, 8 electrons around it, so octet meets, right? Remember, this octet rules only applies to generally what? With the non-metal to non-metal covalent compounds, right? So we have oxygen here too, okay? So we gotta make our first bond, which comes between this carbon to that oxygen, okay? So each orbitals are overlapping each other to form our first bond, okay? We call this, let me put a different color. Our first bond, no matter what, is always called sigma bond, and we put it as a little I don't know. Sigma is like this basically. It's a Greek letter. Okay, sigma bond. Sigma bond. Okay. And then once this dimension is taken over by these electrons, now electrons are repelling each other at the same time too, right? So other electrons who wants to form another bond between two cannot go between these two closest distance anymore. So the leftover of a dimension is this y dimension and this z dimensions to each other, right? So the second bond will come as a, let me actually do a different color so that you could distinguish that. That's two. Yeah, there you go. So our second bond will come from, let's just pick this bond, okay? This orbital. Remember that p orbital they were mentioning about, right? And carbon also has another loop like that with orbitals with electrons in it. Now they form a bond. Okay, I know I drew two sticks, but actually it's one bond. That means these electrons will travel as orbiting like in that dimensions. Okay, not to be interfere with that dimension. Okay, so this is our second bond, and starting from the second bond, we call this pi bond. Oops, pi does not look like that. Pi bond. Okay. Okay. So first bond is always sigma. Starting from second, we call it pi bond. Okay. So we have a now double bond. But now we have to what? Triple bond, right? So we have another dimension that we have to deal with, which is what? Right here. Okay. This is z-axis. Now that we the part of the x-axis, part of the the y-axis are taken already occupied. So now we can have a what? The z-axis. Okay. And these will come together as another dimension. Okay. So this is another two electrons that is circulating around to make a formal bond. Okay. After the first one is always called pi. This is also called pi bond. Okay. So we have a two pi bond here, one sigma bond here within a triple bond. Okay. So then you see these electrons here. Let's kind of think about this way. Okay. You have a magnet. Okay. Plus and minus. Kind of lined up in, so this is going to be one behind it. I'm going to kind of draw it behind it. Okay. Okay, I'm trying to be so we have a three magnets kind of lined up together in such a way, and you're trying to bring another magnet. Well, I mean, I should have in plus and minus, but because just consider that this is like a negative thing, and it's just repelling each other, right? Remember, okay, let's kind of start over. Remember, all the electrons are repelling each other, right? Because they are all negative charged. Because of reason, they want to occupy different dimensions to form a bond, right? We have two more electrons who wants to come in to be part of this. But you can see the electrons are already occupying this space. Is the only way for these two electrons, which is lone pair electrons, right, to exist within it is only this axis right here. Okay, so these two electrons will occupy in this area. Okay, I'm going to put two dots as a looping out all this electron density of a spinning around. So that what I was trying to say here was, if you were to bring another positive side of the magnet to here, it does not want to come together. And for this side, if you want to put a negative side here, it does not want to come together. You want to stay away from it. That's what I wanted to say, because all this magnetic field is repelling the negative on this side and repelling positive on that side. The reason I changed the wordings here is because this all has to do with the negatives only, because electrons are all negative. So, but then now it has a positives here, so kind of makes it a little like a proton, but actually it's not. It's all negative. Okay, maybe I should have said a whole stick of negative charges. But anyways, so this is the basic idea why this such thing would stay as a stick figure, as a linear shape. Okay, let's go into a little more in depth of that. Okay, so now we're going to talk about CO2. Okay, remember CO2 look like carbon in the middle, right? Oxygen on the side. double bond between twos, and we have a two lone pair electrons, right? Okay, I'm gonna draw this a little more quick so that we don't spend too much time on it. We have a carbon in the center. Okay, we have a carbon in the center, oxygen here, oxygen here. Okay, and we have, remember, we always have to have what? Our first bond, right? Coming together is that axis, right? Another bond between two here, coming to that axis. Okay, now you gotta have a double bond, right? So we're gonna take care of, it doesn't matter, I'm just picking randomly, okay? It could have been this axis, it could have been that axis, doesn't really matter. It does not, nothing really dictates which one it should be doing first. Okay, I'm just gonna draw that first. Okay, and there comes that bond. Okay, so this side double bond is taken care of. Okay, let me do the other one on this side too. Let me go with a different color. So in this carbon, this y-axis taken care of with this y-axis, right, which is occupied. Not only have this carbon only has the z-axis to available to make a double bond with oxygen here, right? Okay, now they will come together like this, form that double bond. Okay, now you can see here you have a two lone pairs here and on here, and also here and here, which will occupy. Right now we don't have anything that on, so we don't have anything on this side, right? And anything on that side, anything on that side either. So this whole one, like a fan-looking dimension, is going to be where these two pairs of lone pair electrons are going to be occupying. Okay. So I guess I can draw with this color, where this lone pair electrons are occupying that. And here, now we have another fan-looking thing, but this is going to be what? The z-axis and the y-axis, not the vertical, because vertical part is taken care of or occupied by this double bond area. So you have we have another person coming in. Okay, so because of that reason, we are actually having another whole dimension here, here, and here is being occupied, right? Therefore, you have a lone pair here with the two electrons, lone pair there with the two electrons. Okay, so if you were kind of think about this way, think about you have two chopsticks. Okay, you have two long chopsticks. Okay, and another chopsticks. They're facing each other with toward the legs. Okay, and if you were to kind of shove it in together, meaning that you have chopstick that's with the opening side. I'm going to try to be as descriptive as possible in terms of drawings. So you are sliding those two chopsticks each other. Kind of see where the openings are? As if you are putting two fingers, okay, like index and middle fingers, and then you are trying to slide over each other between the gaps, right? And then it makes that rigidity between two. And you can't really, it's not really easy to bend. That's why it makes this a straight line. Okay, so that's the bottom line of why certain things will shape as a linear. Okay, so now let's get into your question of how the shapes are formed when it comes to bond. Okay, so let's actually do very basic stuff first. Okay, another structure that we drew last time was CH4, right? Okay, it was methane with a carbon in the middle, hydrogen the top, hydrogen all the way around. Remember the central atom, and then this is the one that surrounds. And then we have 4 electrons around and 1 electron each that makes this one bond. And this is also two-dimensional drawing, right? So we're gonna make it much more nice in terms of 3 dimensions. So let's take a look at in terms of our carbon here. Okay, carbon in the center, and then we have our hydrogens. Okay, this regular stick is going to be on a plane, and this is going to be one sticking out of the page into the page. I know you're going to have a hard time imagining that, so I'm going to show you 3-dimensional shape of it. Okay, mole view. you actually would love this site if you are actually into drawing. I don't know who might actually be really interested in drawing these things, but this is a website I go a lot to show a lot of people how things look like. Okay, methane. Okay, there you go. So it's called moleview.org. Okay, you may want to save that. And let me see. There is a different view that I can do, but anyways, I'll just use this one. Okay, so if you look at here, let me actually. There you go. And I want to change this to a stick figure. Oh, there is a way to. Oh, okay, there you go. Model, stick. Oh, that's too thick. Line. There you go. Ah. Okay. Okay. So you can kind of see where you see this. Okay, let me change the color of this pen too, so that you can kind of take a look at that. Okay. So this vertical line and this one is on a plane, which represents this and that. Okay, and you can see this is the one that kind of sticks out of that plane. That's why I use this little line with little, shaded, like kind of popping out of the shape, something like in that direction. So that using that as that representation, and then go into the pages that you're going away from the this plane. So they kind of give you that little kind of fading away, right? And this gives us a shape. If you're to kind of connect the dots, the tips, okay, kind of gives you us this shape we call the tetrahedral. Okay, all right. So that's our first, again, well, probably the second, because we learned the linear. All right. So when you have a central atom with the four things around, it will generally end up being a shape of tetrahedral. Okay. All right. So that will be right here. That's one that we talked about. Okay. We talked about linear also, right? Let's go into a trigonal planar. Trigonal planar is a little bit different concept, and it could be done by another compound called BH3, boron trihydride. Okay, so this, when you actually have a boron trihydride, when you actually draw it, it'll actually look like this. Okay, boron in the middle, hydrogen, 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 all the way around with the stick, 3 sticks. So for us to have a most far away apart as possible is going to be just a planar shape. Okay. All right. So that comes to our trigonal planar part. Now we just have to, now from now on is all about connecting more lines. Okay. In terms of trigonal bipyramidal, it's going to be PCl, Cl5. Okay. Phosphorus in the middle, chlorine all the way around. Okay. And then chlorine has 7 valence electrons if you look at the periodic table. Okay, and then phosphorus has 5. I know I'm not looking at periodic table, but that's what it is. And we just kind of connect the dots to each other. Okay, looking kind of ugly, but if you were to actually draw it simply, oops, no, I don't want that. Simply, it will look like this, basically. Okay, which is 2-dimensional drawings. If you actually come into a 3-dimensional, okay, P is here. We have a straight line of up and down going, and then we have one of them going that, like at 90 degrees here, and we're going to go into angles too. And then these 3 are on the plane, where this pops out of the plane that goes into the plane. Okay, Now what we have here is, let's connect the dots. Look at that. We have two pyramids, triangular pyramids, top and the bottom, right? So we call that trigonal bipyramidal. Okay. Let's go into octahedral. Octahedral is just another compound that has a 6 stuff around it. SF6. Okay, you can already imagine sulfur is going to be the middle, fluorine is going to be on the around, all the way around. So let's just kind of simply do that. 2, 3, 4, 4, 5, 6. Okay, and F is going to be all the way around. Okay, so S in the middle, fluorine on top and bottom. Okay, the other two is going to be coming out of the plane, go into the plane, coming out of the plane, go into the plane. And then you will have this connecting dot shape of can you already see a pyramid shape going on there? Top and bottom. Okay, this is going to be square pyramids, right? Top and bottom. We call this octahedral. Octa means what? 8. There are 8 triangles, 4 on the top, 4 on the bottom as a surface, right? We call it octahedrals. Okay. All right, so that's a basic part of that shapes that you were mentioning about in terms of geometry shapes, right? So let's kind of go with the angles. Let's start from here, okay? You can already imagine this is gonna be a straight line up and down, okay? The drawing is helping makes, oh, I'm glad, okay. So here we have a linear, right? And that linear is going to be always going to be what? 180 degrees right here, right? That's pretty much given, right? And then from here to the plane, that's like a 90 degree. So from here to here, okay, I'm going to just press a drawing like this as a plane, right? This is one whole kind of square planes here, okay? So that would be 90 degrees, okay? From between also, if you look at this from the top view from here, right? Then you have F here, and you have 4 F's all the way around, right? And we have a connection. So I'm going to draw the connections to each other. And we have that line sloping down like this, and as if you're looking at pyramid from top of the peak, right? And then you will see S behind it, right? Right below the S behind it, okay? Right below the F. So think about the connections pretty much easily when you think about geometry. That angle should be here going to be what? 90 degree, right? So everything around this except the verticals where to the plane to plane is going to be 180 degrees, yet from every bonds to bond to each other, they're all going to be what? 90 degrees. Okay. Let's go back to our previous drawing of a what was that one? PCL5. Okay. So we have a, actually, you know what? Let's kind of jump back to our BH3, which were based on this too. Boron trihydride, right? Okay. We have 3 things coming together. That means what? When we are making a shapes, right? Triangles are from the center, divided into 3 sections is going to be what? The whole thing is 360, right? You divide by 3, that's what? 120 each. 120s, 120s, all the way around. Okay? And that would be actually same as what? This part right here, right? That's also trigonal planar type of shape here within trigonal bipyramidal shape, right? Okay, you can kind of imagine that. Once again, you can also see what a straight line here, which should be 180 degrees. Add the electron dots. When we are actually drawing a Vesper, what we call, which is this is Vesper theory, we don't actually draw electron dots on here. But when we are drawing valence electrons, well, what is it? Lewis structures. Yes, it will draw the dots. But in here, when it comes to electrons around the chlorines, they are actually not really that much of a meaningful, because we are only looking at from the central atoms. That's why we don't really draw dots, but it can be drawn. But let me actually finish this up first. So you can already see the plane of the triangle here, and then the vertical they're coming in, and you can already see this is going to be what, 90 degrees, right? So that means what, the bond between two here and here and here, they're all going to be 120s. Okay, so going back to that, the electrons, because we have a lone pair electrons around it, right? So that's how it's going to look like. I mean, maybe I really should have drawn the lone pairs too to indicate that those exist. I just want to be focused on that stick part of that bond first. So I skipped drawing. Anyhow, okay, so that's that part. So going back to that tetrahedral shape, which is going to be what? Let me, since we already have an actual page that showed up here, right? Okay, so that one is a little bit more tricky because it's not really 90 degrees either. So if you look at it from top view, you can already see that's that. However, this is not a bond angle because bond actually comes from here to here, okay? And depending on what we're talking about, the shape changes a little bit, but we're not going that far, I believe. But I actually will show the basic part of it. So this might be actually a pretty good chance to kind of capture these pages so that you can kind of go over. So we went over that linear shape, 180 degrees, right? And then we went into that three-dimensional of the trigonal planar, right? That's a 120, 120 all the way around, okay, which is shown here too. BF3, BH3, same thing, 120 degrees here. And then we went into a tetrahedral. So this is where our angles are a little bit off. All of that, and it is showing as a 109.5 degrees. Okay, which is angle from here to here. Okay, every angle between two sticks, doesn't matter which one you're talking about, they're all going to be a 109.5 as a tetrahedral. Okay, now you may ask, we have a CH4. Let's just follow the same thing. Oops. Okay, that was a CH4 as a tetrahedral shape. What if we have one that's removed? Not as a CH4, but similar but different one, which is called NH3. This is ammonium that we also had a drawing of what? Last time, right? That would look like that with the lone pairs. Okay, so that is as if we remove the one top part of it. Okay, so we have a nitrogen here in the middle. We have that hydrogen there, hydrogen there, hydrogen there, and then one lone pair sitting up. So what happens here is, compared to this bond with the electrons, this lone pair electron takes up more space because they are more freely roaming around the area than when they're bound to each other. So these electrons are suppressing these bonds more lower. That creates, remember this is 109.5 degrees. This angle right here is going to be smaller because this electron density up here. And I think 107.2, 107, that's what I believe, if I'm not mistaken. There is an angle, bond angle, no, that 114.5 is not the one we are looking at. So that would be 107.2. There you go. That angle is 107.2. 0.2 degrees. Okay, so you can imagine this is more electrons. And remember, once again, what the bonds are made out of? Electrons, right? So they are repelling each other. Therefore, this electron density, which is freely moving around, this cloud of electrons are pushing this all in, bonds between nitrogen and hydrogen away from this electron density, creating this lesser degree than this one is. Okay. Another one that we can give an example is water. Okay, because water has 2 lone pair electrons instead of 1 lone pair electrons. Okay, and that is taking another hydrogen away. So we have an oxygen here, and we have 2 lone pairs on that side, on that side. Okay, now you can see when we are looking at the water, which is H2O, a lot of people tend to draw like this. Well, which is not really wrong when it comes to Lewis structure, but really what you really want to do and indicate what the shape actually is supposed to be in terms of chemistry, you want to draw this way, because that tells us this bending part, right? We call this a bent. Actually, I forgot to mention the name of this. This is a trigonopyramidal. Okay, trigonopyramidal and bent. Okay, why is bent? Like I said, once again, this lone pair, 2 lone pair electrons are taking up that space, right? Occupying that space, causing this bond angle to even less than what this was. Okay, I think this is 104.7, 104.5 right there. Okay, there you go, 104.5. So that angle is now 104.5 degrees. Okay, so this kind of gives you a series of different shapes. Okay, all right, so hopefully this is a basic part of the bond angles that you were mentioning about, and the geometry shapes and bond angles. Sure, not a problem, Ash. So I'm actually going to go into a little bit more deeper into that, not more deeper, but more of a topics that initially would cover your exams, which is not that big. Hopefully we have enough time for cover all that. Okay, nomenclature. Once again, we are going into 2 different names by going into ionic compound versus covalent compound. Okay, I'm going to just put CPD. My writing sucks. CPD, compound. Okay, so when it comes ionic or covalent, there is a difference between the namings. Let's just kind of go with the basic with the ionics because they are one of the easiest one. Okay. Okay, we talked about this is sodium, right? And this is chlorine as an actual name as individually. But when it comes to the compound name, when it comes together, we call this sodium what? Chloride. DE. Okay, so INE or whatever that in the behind changes into IDE. Okay, chloride. Okay. K, potassium, let's see. Okay, so this is potassium, right? This is oxygen. But then we call it as, because we have to end as an IDE. This potassium oxide, oxide, where? Yeah, oxide. I just forgot the E. Okay, so let's kind of compare that to the covalent compound. So one you already know is what? CO2. How do you call this? Carbon. We don't say just oxide. What do we say? Carbon dioxide, right? So one of the biggest difference between the ionic to the covalent compound, it ends with same IDE here, 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 right? But the biggest difference is we do not use prefixes here. We have a 2 potassium here, right? We have 2 oxygen here. We did use di, but we don't use dipotassium oxide. That's a distinguishable difference between ionic compound to covalent compound. So no prefix when it comes to counting elements. In covalent compound, we do count. Okay, but we don't put mono here when this is only one. It's a given, so we don't use. But let's just say we have N2O4. Okay, now we have two of them, four of them, and you know that they are both are what? Non-metal compounds, so it goes into that rule. We do count. So what? Dinitrogen. Oops, my writing sucks again. 4, which is tetra. Tetraoxide. However, when there are two vowels coming together, we get rid of that. The counting part of the vowel is taken out and connects to the actual name of the compound. So tetroxide is the correct way of naming it. Okay, so just be as a side note, 1 is mono. I should have done this earlier. Di. 3 is what? Tri. 4 tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. 10 is deca. Okay, well, probably you won't go that far anyways, but yeah. Okay, so this is 1 through 10. Okay, so very easy to do the nomenclatures when it comes to ionic and covalent compounds. Okay, mole concept is pretty easy too. Okay, so when it comes to mole, we have a basic way of going through. Okay, so going from mass to mole, let's just say we have a 5 grams of nitrogen. Okay, and we want to know how many moles there are. Okay, what do we use? We use periodic table. So let's pull out a periodic table. Okay, so last time when we talked about all this things that contains within a periodic table, we talked about this. This is the number of protons. Let me get better color. The number of protons. That's a symbol, the name, and this is was a kind of, we call that mass number, but we also call it as a molar mass. That means when there are certain amount of any elements are combined together, comes together, we call that a mole. Okay, so mole is like a groups of bunch of stuff. Okay, you know how we say 1 dozen is equal to what? 1 dozen, let's say 1 dozen pencils, what? 12 pencils, right? 1 mole of certain thing is 6.022 times 10 to the 23rd of something. We call this Avogadro's number. Avogadro's number. Okay, how you come up with this? There are a whole bunch of stories behind it, but we don't have time for that. But that's basically what it is. So instead of us saying this many number of atoms or molecules, we just call it 1 mole of atom or 1 mole of molecules. Okay, so this is like a little grouping of a simplifying numbers. Okay, so when you have, for boron point of view, when you have 6.022 times 10 to the 23rd of borons massed together, that weighs 10.81 grams. That's just what it means. So all the units that is not shown here for the boron wise, 10.81 grams per 1 mole of boron. That's basically what these represent. Okay, so you look at carbon here, which is 12.01. That means what? 1 mole of carbon is going to be 12.01 grams per mole. Okay, so when we say 5 grams of nitrogen, how many moles there are? So that means what? We have to go to mass to mole by using what? Molar mass. So going from mass to mole and back to mole to mass is going to be molar mass. That's what we use. Okay, so simply 5 grams of nitrogen. Nitrogen weighs 14.1 grams, right? 14.1, 14.01 actually, grams per mole. So we want to be in mole and we want to get rid of grams out of this, right? So what do you want to do? You want to put the grams on the bottom so that you can cancel each other, right? Basic division and multiplication stuff, right? So we put grams on the bottom and we put mole on the top, okay? So it was a 14.01 grams of who? Nitrogen, right? And then we have 1 mole of nitrogen. So we were converting this into that. So that clearly gives us what? Now we can do canceling out that each other. And we have a moles of nitrogen, which is what we wanted because we went to the moles that we want. And we just did the calculations. Okay. So let me pull out a calculator. Okay, so here we go. 5 divided by 14.01 will give us 0.356, well, 0.357 I guess. 0.357. Okay, it's giving me a 10-minute warnings. Okay. 7 moles. Okay. Pretty easy stuff. Okay. Now let's think about this now. Let's go one more step. Okay. We started as a mole, amount of a grams of atom, not a molecule, right? So we're going into atoms now. Okay. Go to that directions. Okay. Remember, we just talked about this. 1 mole is what? 6.022 times 10 to the 23rd, right? So when we are coming from mole to atom, the number that we use, the converting factor that we use is Avogadro's number. Avogadro's number is what we use. Okay? And then the unit goes 6.022 times 10 to the 23rd atoms per mole. Okay, now let's say our next question say how many atoms are there? Okay, number of atoms. Okay, now we continue on here. 0.357 mole of atom, or more of a nitrogen atoms, right? And we'll convert that into a number of atoms. So we want to keep the mole, no, we want to get rid of the mole and we want to keep the atom. So what do you want to do? We want to put mole on the bottom, right? So 1 mole of nitrogen is how many atoms? 6.022 times 10 to the 23rd atoms of nitrogen. Okay, now you can get rid of this unit with that unit. Gotta multiply that together. Okay, I don't think I can do that with this calculator, so I'm going to do it with the other calculator, which I cannot have it on the computer, so let me do it on my calculator here. So here comes 0.357 times 6.022 exponent of 23 is 2.15 times 10 to the 23 atoms of nitrogen. Okay, so you can already tell how we go from mass to moles to atoms by using molar mass and Avogadro's number. And this can go back from atom to mole by using Avogadro's number again, right? You can already see going this as a reverse way. Okay. Let me actually also do the molecules too. Okay. Let me get rid of all this. I wish I can, you know what? Probably it might be faster if I was to rewrite that part. Okay, once again, mass to mole to atom to molecule. Okay, and this was a molar mass, and this was Avogadro's number. Avo number, that's how we'll put it. 6.022 times 10 to the 23rd. And my writing sucks, I know. And the same thing, all molecules to apply the same Avogadro's number. So this will be Avogadro's number also 10 to the 23rd. And let me quickly go into that. So let's say we have 0.5 mole of NaCl. Okay, and we want to go into how many molecules. Remember, this is not an atom, right? This is molecules. You know what, let me actually, yeah. Okay, so then what do? This unit, remember here was what? Atoms per mole on this side. On this side, now we're dealing with the molecules, so we just simply change from, not more items, molecule per mole. Nothing different. Okay, so we're just grouping again. This many number of, so that means we have this many number of sodium chloride will be 1 mole of sodium chloride, right? So we want to get rid of mole and then put the molecules on. So we have to put moles on the bottom, which is what? 1 mole of NaCl is 6.022 times 10 to the 23rd of NaCl molecules. Oops, 23rd NaCl molecules. Okay, so we can get rid of that. And that, you can already imagine, multiply that, and it'll give you whatever number of molecules there are. Right? Let me actually do it. 0.5 times 6.022 power of 23. There will be 3.011 times 10 to the 23rd molecules of NaCl. Now, your teacher can also trick you, try to ask, okay, if you have that many number of molecules of NaCl, out of that, what would be the number of Na atoms? That means what? We are going from molecule to atoms. Well, let's kind of think about it. We have NaCl is this many, 3.011 times 10 to the 23rd. Let me get rid of this screen. All right, this many. And NaCl made out of what? One of that and one of that. That means what? We have 3.022, oh, 3.011 times 10 to the 23rd Na atom, and also 3.011 times 10 to the 23rd chlorine atoms, right? That's how you can tell. Okay, so we should be able to go from here, here, to here, to here, all the way back by using this basic concept of using mass to moles to atoms and molecules. So have a little habit of drawing this, and it will make your life a little easier when you're kind of mixed up. Okay. Another easily ones that we can also finish is a balanced equation too. It's not that hard concept. Okay, that's just a very simple one. Okay. Water is going to formed by a hydrogen oxygen. Okay, so basically what we do is we count and then try to match up. It's like a little puzzle. Okay, we have 2 hydrogen here, 2 hydrogen here, which is happy, but we have 2 oxygen here with only 1 oxygen there. So we have no choice but to what? Increase this by 2 so that we could be 2 of this. Because 2 water means there are 2 oxygens. They made this one happy. Now we have to deal with what? Hydrogen. There are 2 hydrogen already here, but double of it. That makes 4 hydrogens. Then we have only 2, so we have to what? 2 here. So we have what? Coefficient of 2 to 1 to 2 ratio. Remember, there's an invisible 1 there. Okay. So most tricky one is usually going to be carbon related stuff. Okay. I know I'm running out of time, so I'm going to be really quick. So any carbon atom stuff with O2 always going to end with CO2 plus H2O. No matter what. Okay, so what you do is what? You count carbons first. which is 1 to 1. Okay, sounds good. We count the hydrogen, 4 here. We have 2 here. So what? We have no choice but to put 2 in front, which made it 4 hydrogen. That created us to have a 2 oxygen here and 2 oxygen here, right? We have 2 only here, total 4 oxygen. Therefore, we gotta put 2 here. That made it 4. Okay. This is simple. Where it gets complicated is when you're starting having more than 2 carbons. Okay. Okay, this is ethane. Sorry for being quick because we only have you know what? We only have under 1 minute left. I'm gonna do really quick. 2 here, only 1. Put 2. Okay, we have 6 here, 3. That makes us what? 4 oxygen here, 3 oxygen here, right? That's 7. And we only have what? 2 here. And you can't really do the multiple of it. So what I usually do is 7 over 2. And this 2 times 2 is going to be 7. So for us to get rid of that, what you do is multiply everything by 2. They will give us 2C2H6 plus 7O2 plus, go into a 4CO2 and then 6H2O. That's the end.